So let's dig in a little bit deeper here on how circular motion is caused by unbalanced forces pointing towards the center. Any object that's being accelerated requires that there be a force in the direction of that acceleration. Centripetal force is not something new. It's not like we have a new force out there. We only have gravity, electromagnetism, strong and weak nuclear forces. That's it. So centripetal force is not new. It's simply the general name that we give center-seeking forces. So an object that's going through circular motion has to have some sort of forces that are center-seeking. We call those centripetal. Now it can be made up of any number or combination of everyday forces. So everyday forces that we've looked at, we've talked about weight as an everyday force. We've talked about normal as an everyday force. We've talked about friction. Right, we've talked about tension, applied, you name it, just as a general, generic name. These are everyday forces. So when we consider these different kinds of objects that are moving through some sort of circular path, we can look at combinations of these to call those centripetal. Let's look at the moon in orbit around the Earth. Now we're going to study laws of gravity in more detail in later units, but hopefully we know that the force of gravity is the centripetal force that's acting on this, keeping it in its orbit. So this thing is being pulled inward by the force of gravity. So it's got an inward force called W that would be acting on that. Now if I consider a car that's making a turn around a curve there, let's make this a little bit lighter there. The car is traveling sort of outward like this, but is being accelerated inward. If I take a look at an FBD for this, I would see that that's the weight force. I see that's the normal force. In order for that to make that turn, there's got to be something that's sort of pushing it towards the center, right, of that. And as you'll see here, the tires actually push out on the ground. As it's trying to make that turn, the ground pushes it inward this way. And so that force is none other than the force of friction. Now, as long as we're not sliding, that would be static friction, right? So static friction is pointed towards the center, allowing us to make that turn. Now, that's actually the same kind of thing here. If I look at the weight, the normal force, let's make this one a little bit lighter as well. We see that that person is pushing outward on the ground pushes him inward. And again, that would be the force of static friction, provided he's not slipping. Now, when we consider a person on a loop-de-loop, you can see that person right there, they are accelerated towards the center. I'm going to draw a couple of vectors here to make sure we understand what's happening here. The object would be moving around like so. Their tangential velocity would be this way. Their acceleration would be always towards the center, so their acceleration would be this way. Now, I want to look at forces that are acting that way. Well, one of those forces, if I were to draw an FBD, maybe a little bit lower here, one of those forces is certainly the weight of that occupant. So the Earth always pulls down on these objects, so one of those forces would be the weight. The other one, it might not be clear that there's another force there, but it really is, and that force is the force that the track exerts, and it actually exerts a force inward. So that track is also pushing inward on that object. And it's super important that we have a great enough tangential speed that we want the track to pushing them inward. We want that track to be pushing them inward. If it wasn't pushing them inward, that person would sort of like want to fall right out of their seat. They'd be in a state of free fall, if you will. So as long as they go super fast, then we're going to have the track also exerting an inward force on them that sort of keeps them in that seat. Now, when I look at the sum of the forces here, when I go to write F equals m times a, and I look at those forces, I see N and W are both in the same direction. And so I would add them together because they are both pointed towards the middle of that circle. Now, if we consider an object being twirled around in a circle on a string, maybe at the top of this, I'm going to make this again even less bright so we can see this more easily. At the top of this, where the ball is being whirled around, we also have something very similar to what we have over here. We have the weight of the object, so the Earth is sort of pulling down on that, but we also have, provided we go fast enough, we also have the need for the rope to pull inward down on that, and so the tension force would also be acting sort of towards the center. So again, we have two everyday forces that are centripetal. They fall along the center-seeking line. So same idea over here. When I go to write sum of the forces is equal to m times a, those two things are added in the same direction, so I'd add them. Now, when we consider down at the bottom, I want to consider down here. Down at the bottom, I see that we have the weight force that still acts down, but now because my unbalanced force has to be pointed towards the center, what we'll see is that the tension force actually needs to become much larger here. And the reason for that is I need a net unbalanced force always up, right, towards the center, or always down towards the center. When I go to add these things together, I have to have my unbalanced force pointed towards the center of that circle. Okay, so these forces sort of change in response to which way it's being accelerated. Now let's consider a car that's going over a hill. Similar idea here. Let's make that a little bit less bright. This one's always a little bit tricky, so bear with me for a minute. If this car were stationary, so if V tangential was 0, the FBD for this person would be really simple. The weight and the normal force would exactly balance. Okay, so those two would be equal. But if the car is moving, if the car isn't at rest, if it's some value, then in order for this thing to be moving through a circle, we have to have unbalanced force inward. So what happens is the weight will never change. That's how hard the Earth is pulling on me. But in order for me to get an unbalanced force inward, I have to have a smaller normal force, and that's what happens. The normal force will become smaller here so that the person will have unbalanced force towards the center. So you often feel lighter when you're going over that hill. Why is that? It's not because the Earth isn't pulling on you with less force, it's because the seat is not pushing you up with the same amount of force as usual. Now if we consider some rolling hills over here, we have not just going over a hill, but here we have an object that's maybe at the bottom of a hill. Same idea, if it's moving this way, tangential velocity, let me draw that as a dashed line. We don't want to think of that as a force, if you will. We would see here that the weight force and the normal force are again unbalanced, but this time the unbalanced force must be upward, and so the normal force would end up being bigger than the weight, so that I have a net unbalanced force towards the center. Okay, so that unbalanced force must be upward. And similarly over here, we could look at what would happen as I go over that hill. Going over that hill, the weight again would still be the same, W. The normal force would become smaller based on how fast they're going. As a matter of fact, we could calculate, and we will at some point, determine the speed. At what speed? At what V tangential will the car become airborne? Well, what would be the normal force right at the speed at which the car lifts off of that road? The normal force would go to 0 at that point. So that would be the FBD for that car going over that hill such that it just begins to lift off. And when we go to write how the forces, the masses, and the acceleration are all related, we need to be able to look at those FBDs. Okay, so that's sort of our starting point. The FBDs are our starting point to be able to determine how forces cause accelerations.